Okay, here we have a binary star system. So one star and the other star. Orbiting around each other. If they're identical stars, then they're going to orbit around the point in the center. So they have some orbital distance r here, and we know the total distance. 2r is 1.5 times 10 to the 11th. So that's the distance between the Earth and the Sun. So basically, like if the Earth was another sun and they were orbiting around each other, although both of these masses are 2 times the mass of the Sun, so it's a heavier star than our Sun. Okay, so the FBDs for the 2 and the F-net equations are exactly the same, just different direction. So you need to be careful here. Our force is g times the mass of the star times the mass of the star, so that's gm squared, divided by, I called the orbital radius r, so this is the distance between the objects is 2r. You could have called the distance between them r, and then the orbital radius would be r over 2. Well, it's up to you, it doesn't matter. But you have to take into account here that the r squared in the denominator of the force is not the same as the r in v squared over r. So I'm going to use this expression for the acceleration because I'm interested in the period of the orbits. Okay, and I'm going to solve. One of my m's cancels out, but the other one does not. So I get 4 pi squared, and I have another 4 here, so 16 pi squared r cubed over g m, that's the mass of one star, square root, which would be 16 pi squared times 0.75 times 10 to the 11th, or 7.5 times 10 to the 10th, times g times 2 solar masses, so that's 2 times 10 to the 30th kilograms. I'm going to need to take a square root as well. And if I put that in, I get 1.58 times 10 to the 7th seconds. So this is not that much less than a year. A year being about pi times 10 to the 7th seconds. That's 182 Earth days.